everyone. You're watching the second part of the 24th lecture in the series Mathematical Methods for Economics. In the first part, we introduced the concept of a proportional or a relative rate of change as a rate of growth. And now what we're going to do is we will look at some results for the proportional rate of change, which can actually make proportional rate of change calculation for a combination of functions much easier. So let us look at this example, which is taken from the textbooks Etc. and Hammond. Here we have a case of extraction of oil from a well. Suppose both the amount of oil extracted per unit of time and the price per unit change with time t. So let us define x of t as the rate of extraction in barrels per day at time t, and let p of t be the price in rupees per barrel at time t. Then the total revenue for this oil extraction firm is R of t equal to the price times the quantity. So price P of t times the rate of extraction x of t. That is the total revenue in rupees per day. The question here requires you to calculate the proportional rate of change or the proportional rate of growth of total revenue. Now note here, our function here is a product of two functions, the price function and the extraction x of t function. Okay, so let's see how things are going to work. Our proportional rate of change is r dot by r, or 1 by r dr by dt. So we will first calculate dr by dt. Now r of t, the total revenue, is p of t times x of t. Because this is the product of two functions, we can use a product rule of differentiation to obtain r dot, which is dr by dt. And by the product rule, we know that r dot is going to be the derivative of the first function, which is p dot of t, times the second function, plus the first function times the derivative of the second function, which is x dot of t. To obtain the proportional rate of growth of revenue, we're going to divide r dot by r. But let's just give some structure to this expression for r dot first before we move on to the proportional rate of growth of revenue. What we have here, if you notice, is that r dot of t is p dot times x, and I'm just suppressing the t argument because that is just for the sake of presentation here. So p dot times x plus p times x dot. Okay. Let us suppose that p dot, just to give this some structure, let's suppose p dot and x dot are both positive, which is to say that both prices and the extraction, they are increasing over time. Now, this can be explained as follows. So, the price may be increasing on account of inflation. So, P dot is positive. Similarly, this firm might be accumulating equipment to undertake extraction, and in that sense, you can expect the extraction also to increase over time. So, that X dot is also positive. So, what we have here is that because P dot and X dot are positive, that would also mean that R dot will be positive, or in words, this is to say that your total revenue will be increasing over time. Okay, and that increase is, it has two components. One part of the increase in the total revenue is coming from this first expression because P dot is positive. So, this first expression here, P dot times X, contributes to one part of the increase in the total revenue. And the second part of the increase in the total revenue function is coming from this expression here, which is P of t times X dot. So, our assumptions P dot and X dot being positive are vital here for R dot to be positive or for the total revenue to be increasing. Now, the proportional rate of growth of revenue is R dot divided by R. and I've suppressed the t argument again here. So you can see here that r dot by r, so r dot is p dot times x plus p times x dot. So if I divide that by r, which is p times x, the total revenue, then you can see that when I just separate out these two terms, so the x will get cancelled in the first, so you get p dot by p, plus in the second term the price variable will get cancelled, so you get x dot by x, which is to say that the proportional rate of growth of revenue is nothing but the sum of the proportional rates of growth of the two individual variables. So the proportional rate of growth of revenue is a proportional rate of growth of price plus the proportional rate of growth of x. And this then leads us to the result that if we want to calculate the proportional rate of change of the product of two functions of time, then the proportional rate of change of a product is a sum of the proportional rates of change of the individual components. So in general, if you have a variable y which is given as the product of u and v, where both u and v are functions of time, so u is a function f of t and v is a function g of t, then the proportional rate of change in y, which is y dot by y, is the sum of the proportional rates of change of the two individual components, which is u dot by v and v dot by v. So this is the first result that we have with respect to proportional rates of change. Our second result relates to the proportional rate of change of a quotient. And here we have that the proportional rate of change of a quotient is equal to the proportional rate of change of the numerator minus the proportional rate of change of the variable in the denominator. Let us look at the derivation of this result. So if, let's say, our variable y of t is defined as a ratio of two variables which are both functions of time, so you have y of t equal to u of t divided by v of t, then first of all, in order to calculate the proportional rate of growth, I'm going to calculate dy by dt, and then that dy by dt I'll divide by y in the next step. So dy by dt, in order to calculate that, I will use a quotient rule because I have a quotient here, and that is going to be the denominator v times the derivative of the numerator with respect to time, so that's u dot, minus the numerator, which is u here, times the derivative of the denominator with respect to time, which is v dot, divided by the denominator squared, which is v squared. Okay, let's just simplify this a little bit. You can see once I separate out these two components in the numerator, the v will get cancelled, one of the v's will get cancelled in the first term, so that you'll get u dot by v, and the second term will simplify to u by v times v dot by v. I'm just separating out the two v's, so u by v times v dot by v. Now, in order to calculate the proportional rate of change, I have to divide y dot, which is my dy by dt, by y, and because y is nothing but u by v, so that boils down to v in the numerator and having a u in the denominator. So I'll be now multiplying this expression that I have here. And I'm sorry, there is a typo here. This should be a minus here, not a plus. So anyway, so that will be v by u times u dot by v minus u by v times v dot by v. So if I now open up the brackets, you can see the v's will get cancelled in the first term. So you'll get u dot by u, and that's a minus here. So the v and the u will both cancel out for the second term, and you'll get v dot by v. So we have shown here that the proportional rate of growth for a quotient is the difference in the proportional rates of change of the two components that we have in the numerator and the denominator. Let us see some application of this particular result. This is a statement that I've taken from Chiang, an example. So let's suppose we have consumption, which is represented by C, and let's suppose consumption is growing at the rate alpha. Let us further suppose that population H, where H represents the heads, the population age is growing at the rate beta. The question now is, what is the rate of growth of per capita consumption? Now, you would know that per capita consumption, let's denote it by lowercase c of t, that is defined as the total consumption, capital C, divided by the number of heads that we have. That is our definition for per capita consumption. And because you can see it's a ratio, you can either do the calculation that we just went through in the previous slide, or you could simply just use that result and calculate the proportional rate of change in the per capita consumption, which is C dot by C, lowercase c dot by C, as the difference of the individual proportional rates of change. So you have the proportional rate of change in the total consumption, which is capital C dot by C, minus the proportional rate of change in the population, which is H dot by H. And because capital C dot by C is given to you as alpha and H dot by H is given to you as beta, so the rate of growth in per capita consumption, or the proportional rate of change in per capita consumption, is nothing but alpha minus beta. We'll do one more application before we move to the discussion on higher order derivatives. And here we're going to be talking about the relationship between marginal cost and average cost functions. This actually gives you something very intuitive also. So in that sense, I think this application is quite useful. So, and I'll just tell you what I mean by what I'm going to tell you. That's something I'll tell you at the end of this example, the intuition that I'm going to give you. Let's suppose C of Q represents the total cost of producing Q units of a commodity. Then the average cost of producing Q units would be given by the total cost C of Q divided by Q, right? So you have the total cost function, which is C of Q, and C of Q divided by Q. And remember here, to be able to calculate the average cost of producing Q units, your Q has to be positive because you're dividing by Q. Q negative will not make sense, and also you can't divide by 0. So Q, this average cost expression is defined for Q positive. Now let us suppose we look at the rate of change of the average cost when output varies. So this is an example from production theory. Even if you haven't done production theory, it's fine. You are in a position to now understand the structure of cost functions. So if I want to understand the rate of change of the average cost is C of Q by Q, and I want to look at the rate of change of average cost as output varies. So we take the derivative of this with respect to Q. And because this is a ratio, then I'm going to be using the quotient rule. When I differentiate this ratio with respect to Q, I get the denominator Q times the derivative of the numerator, which is C prime of Q, which is nothing but your C prime of Q is nothing but your marginal cost, minus the numerator, which is C of Q, times the derivative of the denominator, which is 1. Divide the whole thing divided by Q squared. Okay. Here I can take 1 by Q out of the system. If I do that, if I take Q out as common, the denominator, then I'm left with C prime of Q as a first term inside the parenthesis, because one of the Q's will get cancelled in any case here, minus C of Q divided by Q. So basically, if you notice here, the derivative of average cost with respect to Q is nothing but 1 by Q times the marginal cost minus the average cost, because C prime of Q is nothing but your marginal cost. C of Q divided by Q is nothing but your average cost. And that is summarized here, that the derivative of the average cost with respect to Q is 1 by Q times the marginal cost minus the average cost. Now this is actually a pretty powerful result, and let's just examine this in a little more detail. Let us suppose, which we already have actually, that Q is positive. Okay, so for Q positive, you can see here that the derivative on the left hand side will also be positive as long as MC is greater than AC, right? Similarly, when MC is equal to AC, your derivative is going to equal 0. and the derivative of the average cost with respect to Q would be less than 0, it will be negative whenever MC is less than AC. Okay. Now, let's just connect this with the shapes of your average cost and marginal cost functions. Even if you don't know the shapes, I'll just follow what I'm telling you, and these are basically U-shaped functions. So, the average cost curve, it first declines, it reaches a minimum, and then it increases. Similarly, the marginal cost curve also, it first goes down, reaches a minimum, and then increases. But if you notice here, one property that you have of the marginal cost function is that it cuts through the average cost function when the average cost reaches its minimum. So, when average cost reaches its minimum, which is at Q star here, marginal cost is equal to average cost. Anyway, that is the basic structure, but even if you don't know that, it's absolutely fine. The point here is that whenever average cost is increasing, so I've shown you a picture just to give you a, sort of a visual and which makes your understanding easier. Whenever average cost is increasing, which is to say DAC by DQ is positive, you can see that the marginal cost curve lies above the average cost curve. That is what you have here. Whenever the average cost curve is increasing, which is to say DAC by DQ is positive, MC is greater than AC. So, MC lies above the average cost whenever average cost is increasing, and whenever average cost is decreasing, the marginal cost lies below the average cost curve. And actually, this is something which, this is something which reflects a general relationship also between the idea of marginal and average. So, for example, when we are talking of average revenue and marginal revenue, when the average revenue curve is going down, when it's falling, then the marginal revenue will lie below the average revenue curve. Similarly, when we compare average product and marginal product, the same kinds of relationships occur. Basically, whenever the average has to go up, the marginal has to lie above the average, has to go up by more than the old average. And let me just motivate this again with an example from our day-to-day lives. Let us suppose you are taking a series of tests, let's say MME tests, and let's suppose you have a given average of marks, average marks so far, and you want to improve upon that average. Now, in order to improve upon that average, and you can take some, hypothetical marks maybe for 3 tests and just see if what I'm saying works, then for your average marks to go up, the marks that you get in the next test, which will be your marginal, that has to be greater than the old average. Then only your average will go up. The marginal will only pull up the average when the marginal is more than the average. And similarly, we can argue for the declining part also. So basically, whenever the average is going up, the marginal has to be more than the average, and vice versa. So this is something, it's a relationship that applies in general as well, and this is the intuition that I wanted to give you. So it will apply to your general marginal and average relationships as well in economics. Okay, so in this lecture, the last part that we now have to discuss is higher order derivatives. This is basically bringing in the idea of your second order derivatives, third order derivatives, and so on till the nth derivative. So let's just quickly introduce this. The first derivative of the function f would be nothing if we have a function f of x, so it will be f of x itself. That's the first derivative. And let's suppose we denote that first derivative by f prime. So if f prime is also differentiable, the derivative of f prime would then be the second derivative of f, which is denoted as f double prime of x. Okay, this is the second derivative of f with respect to x. So that is denoted as f double prime of x, or y double prime, or d2y by dx squared, whichever notation you want to use, you can use. Similarly, the third derivative would be the derivative of the second derivative, so that's f triple prime of x. In general, as we go up higher for higher order derivatives, we just put a number in brackets here, in parentheses here, so that this doesn't look like a power, and y 4 would then mean, with 4 in brackets, would then mean the fourth derivative of the function with respect to x. And similarly, the nth derivative of the function with respect to x would be denoted would be written as y n with n in parenthesis, or fn x. And I think you would be comfortable calculating the higher order derivative. So, for example, if f of x is 10x cubed minus 4x squared plus 5x, then the first order derivative would be 30x squared if we use a power rule, minus 8x plus 5. The second derivative would be 60x minus 8. The third derivative would be 60. Fourth derivative would be 0. Okay, let's now take another example. Let's suppose you have y equal to a times L to the power alpha, where L denotes labor, and here L is positive. Capital A and alpha are both constants. So here you're asked to calculate the third derivative of y with respect to L. So you can see here the first derivative would be a times alpha times L to the power alpha minus 1, again using the power rule. When you differentiate this a second time, you get a alpha times alpha minus 1 times L to the power alpha minus 2, and then the third derivative would be a times alpha minus 1 times alpha minus 2 times L to the power alpha minus 3. So I hope you've got a sense of how to go about calculating high order derivatives. Let's do this problem. It's based on the textbook by Sater and Hammond. It's a pretty interesting problem, so I thought I'll include it in this lecture. This problem says that if n is a natural number, let n factorial, so n factorial is nothing but n times n minus 1 times n minus 2 and so on till 3 times 2 times 1. So, for example, if I ask you to calculate 5 factorial, you'll start with 5, then go down to the next integer 4, 3, 2, 1, and you can see here 5 times 4 is 20, times 3 60, times 2 which is 120. So, the question asks you to show by using mathematical induction that y equal to x to the power n implies that the nth derivative of y is equal to n factorial. Okay, just read the statement carefully. Now, we have to use mathematical induction here. So, just to recapitulate, for mathematical induction, we first show that the result is, we do this in 3 steps. We first show that the result is valid for n equal to 1. In the second step, we assume that the result applies for some general n equal to k. And then as a final step, we prove that if the result applies for n equal to k, it also applies for n equal to k plus 1. And that sets up a cycle of things. So in that sense, it will apply for all natural numbers. If it applies for both k and k plus 1, then it will apply to all natural numbers. Now, as you can see here, the result is in fact valid for n equal to 1, because when I put n equal to 1, what do I get here in the statement? I get y equal to x. And because n is equal to 1, I only have to go up till the first order derivative. So, the first order derivative here, dy by dx, is nothing but 1, and that is our 1 factorial, because n here throughout is 1, okay. So, y equal to x implies that the first derivative is equal to 1. So, clearly the result is valid for n equal to 1. Now, let us suppose that the result is valid for some general n is equal to k, and that would then mean that y equal to x to the power k, because now n is equal to k. So, y equal to x to the power k implies that the kth order derivative of y is k factorial. The kth order derivative of y with respect to x is k factorial. So, we are assuming that this is true, and now we will try to use this assumption to prove that if the result holds for n equal to k, then it should also hold for n equal to k plus 1, right? Now, if n is equal to k plus 1, our statement on the left hand side of the implication arrow will become y is equal to x to the power k plus 1 now, okay. Let us now calculate, work on the k plus 1th derivative of y, because now n is k plus 1, so we have to work on the k plus 1th derivative. Okay. So what we have to prove is that the k plus 1th derivative is equal to k plus 1 factorial. Let's see if that is true. Now, if you notice here, the k plus 1th derivative is nothing but the kth derivative of dy by dx with respect to x. Yeah, because if I take the derivative once for y and then I differentiate it k times with respect to x, that will mean that I am differentiating y k plus 1 times. Okay. So the k plus 1th derivative of y with respect to x can be written as the kth derivative of dy by dx. Okay, now what is dy by dx? That is something we can easily calculate. Y is equal to x to the power k plus 1. So dy by dx by the power rule will be k plus 1 times x to the power k. So our objective now, to see if we get the result, is to calculate the kth derivative of k plus 1 times x to the power k. K plus 1 times x to the power k is dy by dx. Now, because k plus 1 is just a constant, I can bring that out of the derivative expression. So I have k plus 1 times the kth derivative of x to the power k. And notice here, this is beautiful because we have already assumed that the result is valid for n equal to k. Look at the top of the slide here. And when y is equal to x to the power k, the kth derivative of y is k factorial. So here when I calculate the kth derivative of x to the power k, that is going to be k factorial, right? And then we have k plus 1 times k factorial, which is nothing but k plus 1 factorial. So this is where we can use mathematical, this is an application of mathematical induction, and it's a pretty interesting problem in terms of being able to calculate higher order derivatives. So with this, we conclude the second part of today's lecture. I hope you found this lecture useful. Thank you very much.